Hello, my name is Cantilever Truss Bridge, and today I'm going to be talking about Nicogino. Wait, uh, my name is Nicogino, and today I'm going to be talking about my 2025 ENR251 final design project. Um, for this project, I decided to um, build a cantilever truss bridge with the Pasco bridge kits that the college had provided to us. Um, this bridge, I didn't find it. Let's just say it found me. It looked really interesting when I was looking through the couple of the options that we could do with the bridge kit. And I'm really glad I picked it because it led me to some really interesting research, and I got to learn a lot about this really efficient design. And yeah, so I started the project after putting the bridge together, of course, with the help of Dr. Ben. I started with just some general research. I wanted to see if I could find anything in the country that looked similar to the bridge that I had built, and also what its origins were. So I was able to find out that the first erection of a cantilever truss bridge of this style was in 1867 in Germany by this gentleman right here, actually. That's Heinrich Gerber. He was the first one to design the modern cantilever truss bridge and also have it patented. And as far as I could tell, he's also the first one to have one erected. So it was really groundbreaking in that sense. You could see him there showing off the design. So, if we're looking at his simple display here, it actually really helped me do my theoretical analysis, which we'll talk about in a second. But you can see, if we're looking at him, he's putting a moment on these guys like this. And they are acting as the truss, and they are turning that moment into tension and compression. So you can see this man's arm here, these arms here, are going to be in tension, right? And then all the compression is going to be in the lower members here. When you're looking at the bridge as a whole, it's a little bit hard to dissect it like that. But when I'm looking at this photo with Henrich doing the demonstration with his friends, it's a little bit more clear. And then you can see this man's torso. Both these men, their torsos are not under any tension or compression, at least vertically. So after doing that research about its origins, I also did a little bit of research about what its place is in the modern world. The United States is home to one of the largest cantilever truss bridges still in use today, and it crosses the Columbia River. It is the Astoria Megler Bridge. It was built in 1966, and it connects Astoria, Oregon, and Megler, Washington. I would have loved to include a picture in here, but I didn't have quite enough room. The bridge is massive. It has a 2,500-foot free span section, which is quite impressive. So in my theoretical analysis, like we had just talked about, I had said that anything in this direction, anything this support here, actually this picture would be better. For my theoretical analysis, I said that this was going to be in compression, and sorry, that this was going to be in tension. These were in compression, and then that this vertical member here was going to be a zero force member. So I was like, if you're looking at this and comparing it to Henrich and his friends, these are like the men's arms, right? So and then I also analyzed the beams here labeled by 3 and 5 and also 4. These ones were a little bit harder for me to figure out, but using my calculations, I was able to determine that number 4 was going to be in tension. Number 3, surprisingly enough, is actually a zero force member. And number 5 would be in compression, and quite a bit of compression, in fact. So that was my theory. And so after I came up with some of that convention, I got into doing method of sections and trying to come up with a series of equations to model the experiment that I wanted to do. And the experiment that I wanted to do was to simply take a 1 kilogram mass and move it across the bridge. I would hang it in location here, 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 and here. That's 9 locations A through I. So if, you can see that in my table here, but we'll talk about that in a second. So, like I said, after I determined what I thought was going to be in compression, what was going to be in tension, what was going to be a zero force member, I started doing some calculations to see if I could prove that. And I was purposely trying to work without numbers, simply to make this easier to move into octave after I got my system of equations down for the model. This was because I wanted to move to octave. So if I could get this working with a basic situation, I could attempt to look at some more complex situations, of course, right? So in my method of sections, I started with a slice here, and you can see that in this analysis here. Well, actually, you know what I should say is I started with my support reactions first. So I started with the support reaction here, AY, and I went to the support reaction here, BY. And after I got those, then I made my first slice here. So making that first slice, I was able to find the force in this connection from E to C, which was monitored by sensor 5. I was also able to find the force in this beam from F to C, that's monitored by sensor 6, and included in that, for no extra charge, I got the force in this connection from D to F, which I didn't have a sensor on, so you won't see it come up anymore. After I did that, I just kind of worked my way back. My next cut here was going to be through 3, 2, and 4. And from that section, I was able to get the force in the connection from D to A, which is monitored by sensor 4. I was also able to get the force within the connection from C to B, monitored by sensor 3. And I was also able to get the force in the connection from C to A, which was sensor 2. Now, the last member that I had to get to, which a little bit less exciting, I had predicted as a zero force member, would be this member here. And I did that by joint analysis at this joint here, which you can see. So I was able to do that, get all of my equations. I then I made my equations a little bit easier to look at here for you in this in that figure there, but I won't spend too much time on that. I moved those equations in that I moved the equations in this form into octave with one variable, which would be the location. My mass wasn't changing. The only thing that was my location. So I wanted to be able to enter in which location I was interested in looking at the values for, and from there be able to get the output, which would just tell me the force at sensors 1 through 6, and also the support reactions, because they're also important. So to do the output that I wanted, I used a struct, and that struct, in theory, would have made graphing this a lot easier if I got to that point. But here's where we'll start talking about where the wheels fell off on this a little bit. I think I definitely had some mistakes in my calculations, and I think there were some factors that went overlooked that did not allow me to get an accurate modeling of the the bridge and the situation that I was looking at. I think the data that I collected here, you can see in that table, I think that data was valid. It seems to make sense as the weight moves from this side of the bridge to this side of the bridge. As it moves, the load, the support reactions decrease from A to B, which is what you'd expect. And the loads, I was analyzing this truss, the loads within that truss also decrease at the same linear rate as the support reactions. So the loads within the trusses were directly proportional to the support reactions that were being felt from beneath said truss. And the data makes sense to that. As much as I would like to blame it on bad data, I can't. My calculations were able to align enough with the data I collected and my theory to correctly give me the proper convention of force within the member or at said sensor, right? So if I was curious on whether it was tension or compression or zero force, my code could tell me that, but it couldn't tell me any accurate readings for the sensors. So I really didn't pursue it any further, which is why you're not seeing any graph. And yes, I could have graphed the data here, but like I said, it's really easy to see. It's just linear. So, the straight lines wouldn't have really told us much, so I didn't see much value in graphing it. I figured it'd be better just to talk about it. So, yeah, that kind of brings me towards the end of this presentation here. I was able to give you guys some insight on the experiment that I did with the moving mass. I was able to give you a little bit of history on where the cantilever truss bridge comes from and its origins, also where it's used today, and also a glimpse into the process that I followed and what my goals were with said process as far as it went, as far as it goes in relationship to trying to create a model, a model set of calculations for this scenario. So all in all, I'll tie it together here. I think the construction of the bridge went well. It was massive and it was fun to look at. I think the experiment portion of it went well too. Like I said before, I took my time and I calibrated the sensors. I think the data that I collected was valid, and I think that the process that I followed doing the physical experimentation was sound. Could I have done more trials? Yes. Would I have done more trials if the time allowed for it? Definitely. I would have loved to try a couple different masses and play with data that way. But I think my shortcomings really lied within the calculations. Like I said before, I think there were some key aspects to getting those calculations to work that went overlooked by me. So I think with a little bit more time spent with the calculations, I could have gotten those sorted out. And unfortunately, since that was such a core piece of this project, the wheels kind of fell off there. I think my intentions of moving it into Octave and using Octave as a tool to model the scenario was sound. And I think that I would have been able to show off some pretty cool stuff in the end. But my wheels were turning, even though I was not succeeding with the current spot that I was in. My wheels were still spinning. I had hopes to get this modeled successfully with the single mass and the different locations, and then attempt at modeling a couple different types of build materials and seeing where this bridge would fail based off of some real world factors, as in the material it was made out of and its modulus of rigidity, how much weight was hanging off of it and where it was located, and some of those things like that. So if in the future I ever have any time to take a look at this, I think that's the direction that I would go. But I definitely learned a lot through this process, and I had a lot of fun writing the report, and I love researching engineering and design, which is what this project really boiled down to. So I got to learn a lot of cool stuff about cantilever truss bridges, and I can bore some people about that in the future. So thank you for listening to my presentation, and hope you have a good summer. Thank you.